Vamos a continuar con la sesión de hoy y nuestra siguiente plática es con Zamantha Guerrero, eh, quien nos va a hablar de superficies con dirección principal canónica y curvatura prescrita. Gracias.
Hello, everyone. Today I will be speaking about a topic that's very, very pretty, which is, analyzing surfaces and finding some of its properties. So I'm going to be speaking about surfaces with canonical principal direction and prescribed curvature, but mostly, the basic properties of these surfaces. So let's get started. Okay, so we're going to start with some motivation, which is the concept of canonical principal direction started with constant angle surfaces, which was first defined in 2007 by Dylan, Stanenkels, and Van der Weyken. And so they defined it as a surface whose normal vector field was always had a constant angle with respect to some other field. In their case specifically, I believe they worked over the sphere cross R, but the definition holds. So what do these surfaces look like, and why are these the inspiration for canonical principal direction? Well, in 2009, they analyzed that property in R3. And we have what we would expect, which is surfaces where we start along some line on a plane, and we attach along that line lines that have a constant angle along the line. So here we have that constant angle theta, and we're placing them along this curve that's defined by this alpha. So that's one of the possibilities. We can also have a plane, and we can also have a cylinder where it's just the vertical cylinder. So all three of these cases, we have lines attached to some curve, which makes sense. All right. So this is a little model of what that could look like. I just took a random curve here in the plane. In the parameterization that I had given before, I substituted with sine of tau plus 2. And it gives this. It actually looks prettier if I extend the boundaries, but it outer intersects. So I just kept it like this. And well, we're going to use this to introduce some notation. So we're going to call she the normal vector, and the tangent vector, the tangent part of the, we're going to say vertical direction is going to be called t, and this is normalized. So we have the vertical direction, tangent part, t, normalized. All right. So we can instantly notice some things about these surfaces. And this actually is satisfied whether it's in R3 or in any space. Is that t is principal direction. And the principal direction, the principal curvature in that direction is 0. So we might start thinking, okay, so we know that if the angle is constant, then t is the principal direction and the curvature is 0. So is it something that's satisfied in the reciprocal? So we might think, okay, so if t is a principal direction for all points in M, does it maintain a constant angle, or does it say something about the curvatures, the principal curvatures? Well, let's see. Now, this is precisely what we're going to consider the principal direction property, canonical principal direction. So here it is. First, inspired by Frankie Dillon and collaborators in 2008, a surface immersed in M bar has canonical principal direction if the projection of a certain vector field X over the space, that is the T, is a principal direction. So let's just start with some examples so we can get a feel of what that would look like. And then we're going to start analyzing. So this is a graph of what would be a surface with canonical principal direction in the hyperbolic space cross R. It's a specific case where it's flat, and it has canonical principal direction with respect to the vector field tangent to R. And it's, well, we parameterize it like this. We show further on why this is a parameterization, but just for the meantime, so you can take a look at what that looks like. But of course, nowhere does it say that X needs to be a certain fixed, a constant direction or just the tangent to the R. So here is another option where we have a canonical principal direction surface where it has that property with respect to the vector field minus yx 0. So we have little, let me see if I can draw on this. This won't be useful. If not, that's why I brought out the whiteboard. So, not. Okay. So it turns out that it doesn't have to be that specific, that surface specifically. We can take any surface over the sphere, any curve over the sphere. So we're gonna do something like this. And if we trace the lines starting from the origin over the well, something like that, and we project them over here. This surface, what we have here in the middle, has canonical principal direction with respect to the field that I had mentioned earlier, the minus y x 0, and that happens always. And we can see that easily. We just have to take the normal vector field, which, okay, well, I use red, is around here. And we see that when it changes along these lines, well, it doesn't change. So it's a principal direction, and so is the other orthogonal direction. So surfaces can really look a lot of different ways, but we're going to focus specifically on surfaces that have canonical principal direction with respect to a closed conformal field. Okay, so let's go back to the presentation. To view. There we go. Okay, so let's start with this parameterization, and we're going to break it down in a minute. So we say it has canonical principal direction with respect to a closed conformal field X. And we're going to specify all along this talk, we're going to want the normal vector field to never be in the direction of x and also never be orthogonal to x. So that's just going to be constant. I'm not going to be repeating it, but that's just going to be that way. And we see that there exists a neighborhood around which we can parameterize the surface as this form right here. So what does this say? We're going to take a point in N, and we're going to follow along the local flux of the X vector field of certain height. So we go back to here. We have N here at the bottom. We're going to, we have a certain specific curve that I'm going to talk about later. And we are going to take a point along that curve, which has Fermi coordinates with respect to that curve. And all of those points are going to be at the same height according to the flux of that X vector field. Okay. But how do we come to see that this works? Okay. So for starters, we're taking the case specifically where we have canonical principal direction with respect to a closed conformal field. This means that, well, for starters, our ambient space must admit a closed conformal field. So we have that we can, we have a foliation which allows us to, instead of working in N just like that, we can actually work in the warp product. So everything we're going to do from now on is going to be here in the warp product. Before, when we said that we would follow along in the flow of X, well, that's equivalent to just following along to these vertical directions, the directions tangent to that are. Okay, so now it looks just like a normal graph. Good. And we're going to assume that F is going to be that graph from N to R. And what our parameterization gives us is that if of ST, that is, we take that point, which is at a distance t from an initial curve gamma, and we're going to lift it to the same height along all the equidistance. So this is actually pretty easy to see why it's in this way. And it was done by Garnica, Palmas, and Ruiz-Hernandez in 2011. You take the property that the surface has canonical principal direction to prove that it's going to keep the same angle along level curves. So, well, not exactly level curves, the lift of the level curves, but yeah. Now, you might remember, this all started from constant angle surfaces. Now, we haven't found that the angle is constant in the entire surface, but it is constant over those level curves. Then what? Now that we know that it's constant along level curves, it can be shown that F is transnormal. Now I'm going to ask you to just remember that detail because we're going to focus first on some other things, but just keep in mind the graph. If you can see a surface with canonical principal direction as the graph of a certain function F, then F is transnormal. All right. And finally, if F is transnormal, then its curves are, its level curves are equidistant. So just from there, we know that we have to lift them to the same height, giving us the parameterization that had given before. Okay, so now we have some idea of what these surfaces look like, but it's, well, let's keep going. Yeah, so remember that. All right, what can we say about the angle then? Well, not much other than the fact that it's constant along these level curves. Why? Because in R3, we have that surfaces of revolution all have canonical principal direction with respect to a radial field. So, it's a very broad possibility. And in fact, and this is one of the results from my thesis, is that if we have a surface that is tangent to a killing field, then which doesn't become zero, and then it coincides in all points tangent to the surface, then M has to have canonical principal direction. So that leads us to think, okay, so if a surface is kind of a revolution surface, then it has canonical principal direction. The reverse is not true. So if it has canonical principal direction, it's not necessarily a surface of revolution. One of the examples was, well, we already saw that before. Okay. So, good. So that's where we're at. With the angles. But so now the curvatures, which is the other thing we were wondering about at the beginning. Now, the shape operator has this form, which makes a lot of sense. Let's see. Can everyone see my mouse?
Yeah, we see it.
Okay. This makes a lot of sense. Why? We have that the principal curvature in the direction of the direction t, the tangent of the vertical direction, coincides precisely with the curvature of just the curve. So let's go back to the here to our board. So what we have in a general sense is we start with a curve in the bottom. So we have n. We have gamma. And we're going to take all the equidistant curves and we're going to lift them to the same height. So what we're essentially doing is that we're placing a copy of the same curve orthogonally against each point along the gamma. Which, it's it kind of looks like a surface of revolution, except that, of course, the gamma doesn't have to be a circle. All right. Now, the nice thing about this is that when we take this principal curvature, that principal curvature precisely coincides with the curvature of that curve we're placing along that gamma. So it makes perfect sense. It's going to become more apparent when we put the diversion in other spaces. Because this is a version in general, we're working with a RAF product. And the principal direction in the direction of the level curves also makes a lot of sense, because this term is actually the curvature of the gamma, of the level of the equidistant curve. So if we have this point here, in one direction, we have the curvature of the line, and in the other direction, we have the curvature of the other curve that's in the plane. So that makes complete sense. Good. Now, we also have that this norm satisfies this differential equation, which is going to depend on the curvature of n, which means that if we're working on a work product where n it has constant curvature, well, these equations will simplify a lot. And we have this precise. So if the curvature of n is constant, we have that the norm of the tangent to the equidistant curves has this form. And so the previous equation simplifies to this right here. And here we can really tell that it's the curvature. So everything works as one would imagine it should. Okay. So now that we have the shape operator, we can find the rest of the curvatures. Mean curvature, just the sum and divided by 2, and the Gaussian curvature. We have the product of the two principal directions plus this term, which is the sectional curvature of the plane tangent to the surface. Here we again have the curvature of n, and we also have that n is precisely equal to the second derivative of the norm of the derivative of the equidistant divided by its norm. So that comes in handy in the proofs. Okay, so now that we have the curvatures, we have to go to the classics. What do these say about the minimal surfaces, the flat surfaces? What can we say? All right, the first thing we can say is if we have n immersed in a wrap product, and we have that property where it's neither orthogonal or tangent to the closed conformal vector field. And we also have that the mean curvature is equal to some constant times, I forgot to change this here, but this is the angle function, plus another constant. We have these properties. We know that curves equidistant to alpha in n are going to have constant curvature. We know that M is going to be foliated with equidistant curves of constant curvature in space. And we also know that the tangent curves in the direction of these level surfaces are going to be Keeling. So we started out with a surface that we don't know what it's doing. And by assuming that it has constant mean curvature, we know that that surface now has to have also constant mean curvature. So it becomes this, right? And we're going to still be placing some curve here all around. And also we'll also find that the tangent vectors to these equidistant level curves are Keeling fields. So that just brings it home that it's something like a surface of revolution or a cylinder also, because Keeling fields can be also just translations. So this is what we have, and we have constant mean curvature. Now, this is for in a general sense when we're working in an arbitrary rough product. Word product. So let's see what we have if we focus on specific spaces. Here we have an example where we're working in the hyperbolic space cross R, and we're taking we're beginning with a geodesic. And we're using precisely, I don't have it here yet, but this is the solution when we try to obtain that n is minimal. So this is actually going to be more explicit further on, but this is an example of what that would look like. All right. So if we focus on specific spaces, we find, well, in Montagneux and Nister in 2011, that the only minimal surfaces in R3 with canonical principal direction with respect to a constant vector field is going to be the catenoid and the plane. Those are going to be the only ones. Then in 2014, it was found that if the surface had canonical principal direction with respect to the radial field, then it had to be of revolution, which again is consistent with what we had found. Explicit parameterizations for hypersurfaces in Q2 cross R. Here we're talking about space forms with canonical principal direction are given by Tejero in 2010. So in space forms, so it would be one of the examples would be the one I had shown before. And if M is immersed in a space form and has canonical principal and constant mean curvature, then it's globally invariant by a Keeling field, which is also consistent with the new result. Okay. Now, I had asked you to remember the fact that if the graph of F had canonical principal direction, then F was transnormal. We're going to come back to that. So Garnica Palmas and Gabriel Ruiz in 2011 showed that if the angle, again, we have here the dimension of the angle, we're going to take it distinct from pi over 2. If F is transnormal, if M has canonical principal direction, then F is transnormal. We had already shown that. But also, if the graph of F is transnormal, then it has canonical principal direction. So it goes both ways. Then Di Scala and Gabriel Ruiz in 2007 showed that if a surface in a word product has constant mean curvature, then F is a parametric, which is transnormal, and it satisfies this other condition. Well, so another new result is that the reverse is well, not completely true, but if we have F, which is a parametric, then the graph of F has canonical principal direction, and it is foliated by curves of constant curvature. So in fact, it satisfies all of these results. Okay, so Canonical principal direction surfaces and isoperimetric surfaces are very closely related. What else can we say? We talked about mean curvature. Now let's see what happens with Gaussian curvature. So we're taking M in the word product, but in this case, we're going to need N to have constant curvature. So we're going to take it as the hyperbolic space, the sphere, or just R2, the plane. And we're going to assume that it has constant the canonical principal direction with respect to the vector field tangent to that I. Then we assume that it has constant curvature. Okay. Then we can actually obtain the same results that we had obtained for constant mean curvature, except for one detail. It's going to satisfy either all of the points mentioned before. So it's going to be tangent to a killing field. It's going to be foliated by curves with constant curvature in the space and also in N. It's going to be isoperimetric, or it's going to be ruled by geodesics orthogonal to gamma, which is what we might imagine if we were to take a constant curvature surface in R3, for example. Okay, so these are our two possibilities. Good. If further, we also assume that we're not in a word product and we're just in a product space, then we can actually give an explicit parameterization for that surface given a certain initial curve. So we take this initial curve that we're going to need to have constant curvature, and we're going to put these curves all around it orthogonally. And that is a constant curvature surface. Good. Finally, if we take this other property, we're going to assume that either of these two conditions occur. There either exist an A such that when we take the restriction to the surface, the gradient of A is close conformal, or it's I'm sorry, someone, no, okay. Or it's a function defined already over M, and that itself is close conformal. And we can take H and K multiplied by some constants. Then either M is foliated by curves with constant curvature, which are equidistant, or M is ruled by geodesics orthogonal to gamma. So we have the same results as we had gotten before. Now, this result was actually inspired by an article by my doctorate director, Dr. Gabriel Ruiz Hernandez, where they analyzed what happened when the what happened when the mean curvature is restricted to the height function. So they took this and they restricted the position with some constant vector v. Now, what they found was that it was one of three different possible surfaces where the bottom had constant curvature and it was a sort of a surface of revolution defined by a certain differential equation. That's one. It could be a random surface at the bottom and it was a cylinder. That's two. Or it could be a line, and we connect also here a certain curve. So we have these three possibilities for under this condition. So what I did was try to extend that to where it worked, this condition worked for other spaces. And that's how I came to this property, which if we take the distance function, well, its gradient is 1, so it satisfies this condition. And again, it turned up the same result. And it's completely analogous to what they found in R3 because it's, again, foliated by curves with constant curvature, which is similar to the other result, or it's ruled by geodesics, which is similar to this result. So yes, it's completely consistent, and it seems to all work as it should. Well, these are this is my references. And thank you so much for the opportunity.
Okay, thank you so much for your nice talk. Are there some questions, comments here, there? Well, maybe, of course, I have some questions. But more comments than questions. Have you tried to do this kind of things in the Lorentzian case?
Not yet, but I noticed that there are a couple of articles that deal with the Lorentzian case, just a couple. So I know that there's a lot of work to be done in that case. I have ideas for other things that I want to try in the meantime, so I'm probably going to add that. For instance, I was only able to find one article where they started working with canonical principal direction with respect to a Keeling field, and that was one by Tejero. And but it seems like there could be a lot there, and this example is actually one that I was able to come up with, and so I have a general idea of what I would like to do there. So no, yeah, there's a lot still to do.
Mm-hmm. Mm-hmm. Okay, and some other comment. You worked with the space Q times I or I times Q, where Q is a space form. So you have this homogeneous space, but have you tried something with some other homogeneous spaces of dimension 3, like some, say, Berger spheres or something like that?
No, I actually I worked with spaces with general workspaces.
Yeah. So in particular with non-warped metric, but have you tried with some other?
No, not yet. What I noticed is that a lot of the work was being done with homogeneous spaces, of course, but that a lot of those things could be directly transferable to more general spaces. So I wanted to attack that first, but there are also other spaces where nothing's been done. So not yet, but it's to be done.
Okay. More questions here? There? No, if not, let's thank Zamantha for the talk.